Okay, so you are now familiar with this equation now. It's just a ratio of sigma 1 to sigma 3 has to be less than or equal to 3.1. So this guy becomes 3.1 when mu equals 0.6. Walk through all of that previously. And then you apply this sigma 1, sigma 3 for any faulting regime, and you will have what S1 should be in that faulting regime, and that gave us this, right? So now how can we use this to bound the maximum stress states in the different faulting regimes? It's pretty straightforward, and I'm going to show that from first principles, and I'm looking for space. Let's try doing it here for reverse faulting regime. So for reverse, I'm just going to write S capital H as SH max, S small h as SH min. So this is what you have, right? It's at that point when it's about to sleep that this value equals that, right? Before that, before sleep, it's less than. So I'm going to use less than or equal to 3.1, right? And now you already know how to calculate this term, right? So we assume SV is given. It's the overburden stress. That was homework 1. It's just weight of the rock mass and the fluid in it. That's what gives you this. So you know this. You can measure this, right? So what you don't know is SH max. We have never had a conversation on how to calculate it, but I hinted that you really can't get it exactly, but you can find bounds on, you can define bounds on SH max, and that's what we're going to do using this equation. So you know everything except SH. So make SH the subject of the equation. Multiply both sides by this, gives you what? SH minus pore pressure is less than 3.1 times SV minus pore pressure. So we have just multiplied both sides by SV minus pore pressure. And now SH is less than or equal to, so you take minus pore pressure to the other side. It becomes plus pore pressure, and you have 3.1 times pore. You have minus, you see there's a minus here, right? Minus times 3.1. So was 1 minus 3.1, it becomes 2.1, right? So this is 3.1 SV minus 2.1 pore pressure plus PP, move to the other side and took 1 out of the minus 3.1. And what's this? It's saying SH max has to be less than this value, which we can evaluate. So it gives you what type of bound on SH max? An upper bound, right? It has to be less than that value. So CFF, Coulomb frictional faulting theory, helps us establish an upper bound for SH max in the reverse faulting regime. How about in the normal faulting regime? We go about same calculation, SV minus pore pressure. So we use this equation, right? Because S1 and S3 have changed. SH minus pore pressure. Small sh again, small h means it's minimum horizontal stress. It's going to be less than 3.1. All of this is 3.1. And you already know SV, right? SH min is what you're going to try to bound. So make that the subject of the equation. How do you do that? Multiply both sides by SH minus pore pressure. So you have SV minus pore pressure is less than or equal to 3.1 times SH. So you're multiplying 3.1 by this, right? And it's going to be minus 3.1 times pore pressure, right? You're trying to make this the subject of the equation. So take this to the left side. It becomes SV plus 3.1 pore pressure minus pore pressure. So that's going to give you what? Plus 2.1 pore pressure. So this is greater than that, so we can write it as SH is greater or equal to SV plus 2.1 pore pressure divided by 3.1, right? All of these divided by 3.1. Again, you know SV, you know pore pressure. So we've established a lower bound for SH mean. SH mean has to be, is greater than or equal to, right? Has to be to the right of this value you will calculate. Value to the right. So that gives you a lower bound. So CFF establishes a lower bound for SH mean in the normal faulting regime. In the reverse faulting regime, it establishes an upper bound for SH max. Maybe I should write it in full now. Very important. And you will see how we'll use that in stress polygons shortly. For strike slip faulting, you can go through the same kind of calculation, but now you don't see SV here, so you actually have two values you don't know. But you can get this from leak-off test, right? Because you know when you try to fracture a rock, the least principal stress is the stress that has to be overcome before you can open up the fracture, right? So just when you open up the fracture while pumping in fluids, the pressure of the fluid in the fracture will be equal to SH mean at that point when the fracture begins to open up. So from leak-off test, from fracture, hydraulic fracturing, just that onset of fracture propagation, you get SH mean. And later we'll talk about the fact that you can get it from drilling induced tensile fractures too. And again, everything is based on the fact that you are injecting fluids. You know the pressure of the fluids you are injecting. At that moment when the fluid begins to go into the fracture, meaning you are beginning to create a fracture, the pore pressure in the fluid equals SH mean. Then you will be able to calculate a bound for SH max given SH mean. But in general, we just say what you get from the strike slip faulting is not an upper or lower bound like in these previous two faulting schemes. What you have is a bound on this ratio, right? And that bound is that ratio will be less than or equal to 3.1. And on the next slide, you will see that this bound which we had established, this one right here, let me use a different color so it's easy to see. This bound we had established for the reverse faulting regime actually simplifies to about 0.6 SV. So this goes away and it becomes SH is approximately going to be equal to 0.6 SV just when the fracture begins to slip. How do we get that? We got that by assuming hydrostatic pore pressure. So if you have hydrostatic pore pressure, PP in psi per foot will be 0.44 psi per foot, right? Pore pressure. SV for that case, which we said was on average 1 psi per foot. You're going to see that on the next slide, but since we have the equations here, it's easier to have that discussion here. So what's pore pressure over SV? Pore pressure over SV will be 0.44, right? So it's 0.44 divided by 1 psi per foot. So pore pressure over SV equals 0.44. And that means pore pressure is actually just 0.44 times SV, right? And if you substitute 0.44 times SV into this constraint, so what you now have is SH, maybe you can clean up some stuff here. So what you have now is SH is less than or equal to 3.1 SV minus 2.1 times what? 0.44 SV. So everything is now in terms of SV. And when you evaluate this, meaning 3.1 minus 2.1 times 0.44 is approximately equal to 0.6. And we say SH max is approximately equal to that at the point it begins to sleep, right? So when it is precisely equal to that value. And that's how we got that on the next slide. A similar substitution can be done for the normal faulting regime using this criteria we got here. Substitute 0.44 SV here, and now this whole right hand side evaluates to about 2.2 SV. So SH mean is approximately 2.2 SV at the point where the fault sleeps in a normal faulting regime. But we don't have that kind of analysis for strike slip because it isn't a function of SV.